So in this problem, we're going to write the rate law implied by a simple mechanism, and this mechanism has a slow first step. So the important thing to keep in mind when we look at a mechanism like this is that the rate law can be deduced from the elementary reaction. So for the first one, we can see that there is one NO2 and one F2 are the reactants. So the rate of reaction 1 is just equal to the rate constant for reaction 1 multiplied by NO2 to the power of 1 multiplied by F2 to the power of 1. And this is the slow or rate determining step. For step 2, rate 2 is going to be the rate constant of reaction 2, and then we just have to have a look in here. It's going to be the concentration of fluorine. There's only one fluorine, so that's raised to the power of 1 multiplied by the concentration of NO2, and again raised to the power of 1 because there's only one of them in that elementary reaction, and that is going to be fast and will not be the rate determining step. So what that means is that the rate law for the reaction is always equal to the rate law for the rate determining step, and that's that guy there. So the first thing they ask us to do is to write the balanced chemical equation for this reaction mechanism. So I've got to add together those two elementary reactions. So NO2 plus F2 gives NO2F and F. And then in the next step, we've got F plus NO2 gives NO2F. So we want to check to see if we can cancel out any intermediates, and it looks like we've got the F here cancelling out, and then we collect together where we have multiple occurrences of the same thing on a particular side of the arrow. So we end up with two NO2s, and then we also end up with two NO2Fs over there. And I'm just going to double check everything and make sure that it all balances. Two nitrogens, four oxygens, two fluorines, and 2 times 1, 2 fluorines. So it looks good. And then it says write the experimentally observable rate law for the overall chemical reaction. And so we already did that. It's going to be K multiplied by NO2 to the power of 1 multiplied by F2 to the power of 1. You don't have to put those powers of 1 in. And we always want to make sure that the only concentrations that appear in our rate law are reactants in the overall equation, which we have. So we're going to call that one good.